Hi, this is Nicole Ostertag talking to you about LNG, liquid natural gas, as a locomotive fuel source. As discussed in Part 1 of this assignment series, liquid natural gas, or LNG, is a viable technology for fueling locomotives. LNG can be used in lieu of diesel fuel, which is the current supply method for all locomotives today. Today, the industry fuel spend is over $11.5 billion a year, making up over 23% of the railroad's bottom line operating costs. The interconnectedness of this industry by interchanging locomotives between Class 1 railroads will necessitate a full implementation and industry standard if LNG is going to be successful in penetrating the rail industry. There are several technology options that are available in the locomotive engine sector and the fuel tender sector as well to make this technology viable for the rail industry. The first of which is 3 different options that are being currently reviewed for the locomotive engine itself. The first of which is a 100% LNG-fueled locomotive engine. However, there is some uncertainty with how LNG will perform, and there's some desire in the industry to have a small percentage of the fuel come from diesel that they know is reliable and can perform if there were any incidents with the LNG fuel supply. As a result, 2 alternatives that are similar to ethanol blends you may see at the gas pump, the E87, E85 options, would be considered as viable options. The first of which is a 95% LNG fuel supply with a 5% diesel fuel supply. The second of which is an 80% LNG fuel supply with a 20% diesel fuel supply. Another piece of technology related to the LNG implementation is the fuel tender. The fuel tender is the method for storing the LNG fuel that is required due to the energy density ratio comparison of diesel fuel. More LNG is required to be on hand to achieve the same length of haul distances that railroads are accustomed to today. As a result, railroads are looking at creating a full cryogenic tank car that would trail the locomotive and house more than 25,000 gallons of LNG fuel. Additionally, those same suppliers of tank cars are looking at building cryogenic ISO tanks that are essentially an intermodal container that has the same cryogenic tank properties as a full cryogenic tank car, but is a slightly smaller version and portable that can be removed on and off a flat or wheel car. Next, let's take a look at what is still needed to get this technology implemented in full scale in the rail industry. The first piece is public policy implementations. Currently, there are some regulations related to a PHMSA ruling that designated highly hazardous flammable trains in a ruling in 2015. This ruling stated that there must be extra precautions taken with any train that contains more than 20 rail cars of hazardous material. LNG is also classified as a hazardous material. This provides complications that would result in more of those trains being subject to this additional PHMSA ruling. Additionally, there will be new rules about what cars can ride directly behind the LNG fuel tender car. One of the biggest uncertainties is natural gas pricing stability. With the changing fluctuations in the crude oil market, the industry is especially cautious about betting that natural gas prices will stay so low for the long term. Considering that a locomotive has a 50-year lifespan and there are over 25,000 locomotives in the industry, this is quite a long-term project that they would be undertaking, and natural gas pricing stability is a big uncertainty. Additionally, there are some adjacent technology innovations that need to occur for this to be implemented well. The first of which would be LNG fuel stations. These currently do not exist for the rail industry, and diesel fueling stations are strategically placed across the network based on the average length of haul that a diesel locomotive can move on one tank of fuel. New LNG fueling stations would have to be placed throughout the network based on the new LNG fuel capacities. That would create additional costs and retooling of the entire rail network. Finally, technologies are being worked on to create what they call toolkits to retrofit the engines rather than having to build completely new engines. This would save on average $3 to $4 million per engine. Let's take a look at the cost implications. First of all, the locomotive supply chain overhaul would be quite expensive. As discussed earlier, the industry fleet is over 25,000 locomotives. To replace each one of these today is in between $3.1 to $4 million. the average estimate to replace or create a brand new LNG locomotive is $1 million in addition to that cost. That puts the cost of each locomotive between $4 and $5 million. Additionally, all of the technology for fuel tenders is relatively new. The cryogenic tank cars, as a result, are quite expensive and hard to produce. Finally, the fuel stations discussed in the previous slide are estimated to cost roughly $4 million each. Based on the average length of haul that can be achieved with natural gas versus diesel, these would likely have to be placed more frequently throughout the network unless the fuel tender size exceeds 25,000 gallons per tank car. Additionally, there are several unknown costs, such as the maintenance costs and the training costs to teach employees how to work on both diesel-fueled locomotives and LNG-fueled locomotives. Potentially, there could be cost savings here in the future on the maintenance, however, that is unknown today. One of the bright spots in the cost sector is that the average gasoline price today at $3.97 per gallon for diesel fuel would drop to approximately 48 cents per natural gas equivalent unit. This could save the industry approximately from $11.5 billion annual spend all the way down to $1.4 billion annual spend, a significant savings of almost $10 billion. With all of these technology and financial hurdles ahead of LNG's integration into the rail industry, how does a railroad or locomotive manufacturer move forward with a successful rollout? I'm recommending using the ADKAR strategy that's found in our human change management slides from our class. This focuses on awareness, desire, knowledge, ability, and reinforcement. My suggestion is that companies focus on the cost takeouts that the company will benefit from in the bottom line profits and the carbon emission savings that can be attained by switching to LNG. This way, customers and employees will both be aware of the issues and the benefits, as well as have a strong desire to change those, both to save money for the company and to improve our planet. The next key to success will be extensive training for all parties on how to communicate about the initiative, maintain and run the locomotives, as well as react to any situations that could result from using LNG. Likely, outside consultants who are experts in developing the new standards would need to be used to train the employees. This would cover the knowledge and ability sections of the human change strategy. Finally, we'd look at how is this going to be reinforced. Today, Union Pacific and other railroads use standard operating protocols, or SOPs, to create rules for our operating employees as well as our administration and management employees. These SOPs would need to be updated for new LNG standards. Additionally, we have managers of operating protocol, or MOPs, who provide periodic reviews and training for all of our employees as well. That would help reinforce all of the training that had been accomplished in the previous stage. In conclusion, it is clear to see why each agency has developed a varying timeline related to the implementation of LNG into the locomotive and rail industry. For example, you can see on this slide the U.S. Energy and Information Administration, the EIA, has developed different scenario plans that state by 2040 that LNG will either account for as little as 16% of the energy consumption from railroads or as much as 95% of the energy consumption from railroads. It is my opinion that after evaluating several scenarios, it is likely that the technology continues to advance at the recent rate of study, which will mirror more closely the low rail LNG red line that you see on the graph above. This would be alterable if one of the different hurdles that was discussed earlier was overcome, that either being public policy or natural gas pricing stability. In order for the technology implementation timeline to accelerate, a significant reduction in risk, also related to the natural gas pricing, would need to occur either by a new technology discovery or a government policy mandate being put in order to push this very conservative rail industry to make a more rapid change.